Okay, so thank you for coming. So I'm Akio Tomiya from TWCU, Tokyo Women's Christian University. That sounds weird, but in Japan, we have a lot of women university. And today I'd like to talk about JuliaQCD, that is calculating subatomic world. So this is a self-introduction. I am a particle physicist, and I'm working for lattice QCD, which I will talk about. And I personally working for kind of distribution of Julia in Japan, and I held several small workshops in Japan since 2021. And this is outline of my talk. So first, I'd like to introduce the lattice QCD, and next I will talk about why we make that new code. And third, I would like to introduce the JuliaQCD and what it is. And I will mention to them benchmarks, and I will summarize my talk. Okay. So what is lattice QCD? So first of all, I should say something on the QCD. QCD is an acronym of the quantum chromodynamics, which is a fundamental theory for particles inside a nuclei. This is a theory for quantum anybody, and this is relativistic, and particles are strongly correlated. So that means that this is one of the hardest problems on the world. And why QCD is important? So QCD is very relevant to describe our world because it is related to the origin of the mass. So our body made from atoms, right? And most of the mass of them are coming from the proton mass or neutron mass. And say proton mass is 2,000 larger than the electron mass. And the proton is made by 2 up quarks and 1 down quarks and massless gluons. But so mass of the quarks are very light. That is just 30 times larger than the electron mass. And actually, the mass of the proton is coming from the mass of QCD dynamics. So to understand that this original mass, we need to solve the QCD. And QCD is, how to say it? Actually, we cannot solve by hand, so we have to use the numerical simulation. And QCD is a theory, how to say it? To calculate the QCD, we have to solve the 4-dimensional Poisson equation a million times to get one physical observable. So that is very hard. And core kernel of QCD is so-called D/. This is 8.4D stencil, bandwidth bound. And the dominant part of the calculation is a huge linear equation with D/. So actually, D/ is just a huge sparse matrix. We have to solve a linear equation many times. And scale of the computation is scale of the computation is very large. So lattice QCD accounts for the over 10% of the annual computation time on the leadership class supercomputers in the several countries. And across the HPC community, its computational footprints on par with the CFD and climate simulations. And this is a list of the users of supercomputers. So the top is that the Frontier in the US. So and several groups uses this machine. And Aurora also in the US that uses the US QCD. And Fugaku is in Japan. And JuliaQCD, PAX, and HAL QCD uses the supercomputers. So lattice QCD is a very important problem, and also requires a huge numerical resource. So I can say that the lattice QCD is a kind of Formula One in the scientific computing because that it requires a huge numerical resource. And if we succeeded to simulate using one of numerical methods, using for lattice QCD, we can say that that numerical method works for everything. So it is important to work on the lattice QCD to establish new numerical methods. And this is a kind of a sketch of the what is a lattice QCD actually. And this is the integral on the top is that quantum expectation value, and this is nothing but just a multidimensional integral. So the size is at 10 to 11. So that is hard to integrate by hand, but the computer can do that. And we evaluate this numerical integration using Markov chain Monte Carlo. And this is a sketch of the Markov chain Monte Carlo. First, we prepare the quantum field and evolve using some numerical algorithm and get a new sample of that. And we repeat this procedure again and again. Then we can sample a lot of quantum fields. Then we can evaluate the quantum expectation value using these samples. And we use the HMC, hybrid Monte Carlo, or Hamiltonian Monte Carlo. This is a de facto standard algorithm to calculate QCD. This is just you can imagine that this is just a random momentum plus EOM. This is just a kind of Langevin motion or a random walk for the quantum field. And then if you get a lot of samples, we can calculate the numeric quantum expectation value using this equation. And during the Markov chain Monte Carlo, we have to solve this kind of equation. This is so-called D slash, and the dimension is 10 to 9, so that is very huge. But we have to solve this equation for each numerical step. So this is very hard. And outcome of lattice QCD is very impressive because that it can predict that which temperature will melt neutrons or protons. Or we can calculate the attractive force or repulsive force between nuclei, or we can calculate some candidate of dark matter. Okay, so this is the introduction of lattice QCD. Next, I would like to introduce the why we make this JuliaQCD. So this is a kind of background. So lattice QCD formulated on 1974. This is actually last year. It was a kind of anniversary year, and there are several codes written mainly by C++, as you can see. And so why we need to make new code using Julia? So this is the reason. So lattice QCDs are one of the formulation for theory, but in physics we have another field, so-called experiment. And we have a lot of plan to future experiment that requires that very accurate number from theory. And but we actually hit to some limitation for the numerical or hardware. So I mean hardware. So so we need to make a new algorithm to get precise numbers. So recently we working on machine learning because that machine learning can use to calculate some numbers in lattice QCD as a surrogate model. And I mean, so we need to test the applicability of machine learning. But the problem happens because that lattice QCD is expensive, as I said. So that usually we use that Fortran or C++ to calculate these numbers. On the other hand, machine learning uses Python. That is it has a speed issue. So of course we can combine them, but problem happens when we debug the code. So we want to perform simulation with lattice QCD plus machine learning without two-language problem. So Julia is, I think, the only solution of that. And why we make it with Julia? So there are several reasons, and I think that you can imagine that. So first of all, that Julia is a LLVM-based JIT, and it achieved that Fortran or C-level speed, preserving that REPL type interactivity. And also the good point of the Julia is that portability. So if you make a code using Julia, you can perform the calculation on supercomputer or notebook or laptop, wherever. So this is very convenient for me. And also rapid prototyping is very good feature of Julia. And also this is personal things, but many legacy code has a problem for the compile. So if you type make, then so you will see that the error message. So that is very hard for us. So we need, so on the other hand, Julia doesn't have such kind of thing. So this is, personally, I think this is a good point of Julia. Okay, next I move on to the introduction of JuliaQCD itself. And JuliaQCD is a name of the project, and which has a lot of sub-packages. And basic stuff is a gauge field.jl that's capable with the SUN regroup gauge field. And on the top of that, and we have lattice Dirac operators.jl that's capable with the Dirac operator, or D slash, I should say. And we have QCD measurements that's capable with the measurement or calculation of the physical observable. And we have lattice.QCD.jl. This is just a wrapper, but this is how to say, which has a good interface, and also the, it has a good wizard for parameter file. So without any pain, we can start lattice.QCD calculation using lattice.QCD.jl. Okay, so this is a number of star history of lattice.QCD.jl. So the number or users are getting increase and increase. And also the several studies are reported in the Lattice International Conference in the last year. And also, the JuliaQCD gets some software award this year. So I think that so many people are, how to say, pay attention to this software. Okay, let me show the demo of JuliaQCD or lattice.QCD.jl. So install is very easy as other Julia codes, and without any problem, we can install the code and make a parameter file using parameter file wizard. Just type the run wizard, and there are two modes, simple and expert. And if you choose that simple mode, then you can just repeatedly type enter. Then parameter files is automatically generated, and then you can start the calculation. So this is done in 5 minutes. So this is impossible for the other codes. So make takes many time, much more longer time than this code. Okay. And there are several works, but okay, thanks. And there are several works, but let me introduce my work. And I published one paper last year, well, this year, I should say. And we calculated topological charge of gauge ensembles. And this work has been done in more or less 1 month because of the portability of Julia. I can run same code in different places. So this makes the calculation time shorter. So Yeah. Okay, let me introduce the benchmarks. We performed several benchmarks for different machines. So benchmarks, number one is, this is my main benchmark. This is the calculation test for the GPU, CPU. And we calculated the operation of D slash. This is just a matrix vector multiplication, but this is a good indicator of the performance. And we performed this calculation on Pegasus and Miyabi. Pegasus is the Intel Xeon machine with NVIDIA H100. And Miyabi is also NVIDIA machine, but the CPU is at Grace. And we changed that temporal direction size. And the benchmark 2 is for MPI, and also benchmark 3 also MPI. Difference of this MPI test is at a machine. So we performed the calculation on Yukawa 21, that is Xeon. And benchmark number 3, we performed the benchmark on Visteria. This is Fugaku compatible CPU. And the final one is that benchmarks on this machine, they compare to the other code. This is the benchmark result. And the CPU execution time goes linearly with T. This is ideal scaling. This is okay. And also the GPU execution time stays on almost flat, actually. But the GPU version can be faster, order 10 times. This is not reached to the hardware limit. This is essentially same plot, but vertical axis is the gigaflops. And with a single GPU, we deliver the equivalent of roughly 40 CPU cores. And the GPU, JuliaQCD single GPU kernel not operating essentially at the practical performance limit, because that it can be 10 times faster according to the hardware limit. Okay, so this is the second example of the benchmark. So we calculated inverse of D slash. This is done by conjugate gradient solver. And plot on the left is that the absolute execution time, and on the right is that the relative speed up for among the number of process using MPI. And you can see that it scales ideally and it works correctly. So MPI works correctly. And also this is a similar result with Visteria. So this is Fugaku compatible one. This also works well. And the final benchmark is that benchmark on this laptop. And I compare with the C++ and Julia. And lattice size, the system size is quite small, but it scales similarly. So that means that the JuliaQCD is not so slower than the C++. More or less same speed, I think. Okay, let me summarize my talk. So JuliaQCD is one of a package for lattice QCD, and it actually runs on any kind of architecture, Raspberry Pi or Mac or Fugaku or GPU machine, whatever, and easy to start. You can start in 5 minutes without any difficulty of compilation or build, and it has a good scaling. It shows good scaling for parallelization. And we implemented most of the modern architectures, modern formulations. And I think Julia is a good choice for most of lattice QCD researchers, because most of us need a quick trial loops for the research. Okay, that's all. Thank you very much.
All right, we have some time for questions. Here we go. Thanks for such an amazing talk. I was curious, have you been able to compare the performance of Julia lattice against the standard C++ packages in HPC grids?
No, we haven't done yet. So this is just, yeah, actually that we have to, how to say, it is difficult to prepare the same algorithm and also same parallelization. So we need to do that, but it takes time.
I see, and there isn't any, like, I mean, I'm an experimentalist, so I'm not as familiar, but is there any standard benchmark, like calculating the pion mass or something like this, where you can have a direct comparison between how fast your code runs and how fast some previous C++ packages have been able to calculate a standard observable?
Let me see. So this code actually has a different implementation for several Lie group. That is actually essential. So it is difficult to yeah, in some detail reason, so it is difficult for direct comparison between them. Yeah, of course, that if we, yeah, in principle, we can do that for some specific parameter regime, for sure. Yeah, in practical reason.
All right, anybody else? No. Oh, one more.
So you solve these large linear systems.
Yes.
Have you investigated, do you write the linear solvers yourself, or are there like packages in the Julia ecosystem that are like, that you pass your sparse matrices to that then do the hard work of solving the linear systems for you?
Actually, good question. So in our packages, we use that linear solver a lot of places, and most of them are used that Julia, how to say, built-in solvers.
But you implemented them yourself in Julia. It's not like you're not using like the iterative solvers package in Julia, or there are a whole bunch of packages in the Julia ecosystem.
Yes. So for example, to calculate the eigenvalue, we just use that RNOD. But most of them are, how to say, just use that linear solver.
All right, if there's nobody else, then let's thank Aki one more time.